I'm Giulio Franzese, and today I would like to discuss with you about generative diffusion models, a topic we are currently researching with Professor Micchiardi. And this work is supported by Huawei under the NetCeption project. So this is the brief overview of my talk of today. It is divided in three main parts. In the first part, I will briefly introduce generative modeling and density estimation. And actually, I will spend a really short amount of time on explaining what are stochastic differential equations, the very basics, the most fundamental tool for understanding everything in this presentation today. And then I will introduce our perspective on generative modeling, that is through the generic lenses of optimal transport. And I will show how it is possible to, briefly show it is possible to interpret famous models like generative adversarial networks or other models like Schrödinger bridges as different ways to solve the same optimal transport problem. Finally, once we have introduced the Schrödinger bridges, I will focus on score-based or diffusion generative models that I like to present as a particular case of Schrödinger bridges. And I will, of course, explain the key ideas, but also I'd like to give some intuition about practical methods to implement these models, to give a link between the world of theory and the actual implementation. And finally, as it is obvious, I will discuss about challenges, possible future works, and so methodological advances or the concept of multimodality. Okay. So without further ado, let me jump to the generative modeling and density estimation. And generative modeling, in a nutshell, is the following problem. So let's suppose that we have a data set of observation xi, n observations, where each data point is sampled from a data distribution PD. And the problem of generative modeling, that the goal that we have when we want to do generative modeling is twofold. So we would like to be able to do density estimation, that is to be able to estimate the density of a generic X tilde, given that we observe the data points. Notice that we say in the literature, if you read the literature, you can have likelihood density as synonyms. And the other goal is to be able to perform generative modeling, that is to be able to sample new data points from the same underlying distribution. As a practical application, we could have the problem of anomaly detection. And this is achieved by doing density estimation. So at testing time, if you observe a new data point X tilde, you compute its likelihood, and depending on its density, you declare whether it's an anomaly or not. Or there are a lot of applications where it's useful to produce unseen realistic data to be able to generate new data or interpolate between observed data, and this is the generative modeling part. Okay, so if you have to understand the three ingredients that you need to understand, that you need to have to understand this presentation are a basic understanding of what a stochastic or a ordinary differential equation is. And thankfully, this subject is very well known and very well studied in the literature, and so we will build on that. Then you need to understand that we use neural networks, but just in the sense that we use flexible parametric functions. So this will allow us to build a stochastic differential equation, flexible stochastic differential equation and ODEs. But really, anything I say today about neural network could be true also with other parametric functions. Why do we use neural networks? Because they perform well in practice. And then finally, you need to understand how to be able to integrate numerically these SDEs or ODEs to translate the thing into a practical discrete time algorithms, because as you may know, it was almost never the case in which SDEs can be solved analytically. Okay. So the kind of stochastic differential equations we consider today are the PoliTo SDEs like in Form 1, where we have the value of a stochastic process x of t is described by this differential. So I'm just going to give a brief introduction to the concept. Let's neglect for the moment this second term here. What you have is that the value of a stochastic process, that could be the position of a particle, or actually the value in our case would be the value of an image, is driven by a given drift, by a given force, f of x of t, possibly time varying. If you want to include also some element of randomness, one way to do so is to consider a Wiener process, the differential, and so to include also a stochastic part in the evolution of this particle, of this value x of t. So this is a high-level introduction of what a stochastic process is in practice. Of course, this is an informal introduction, and in the related literature, the definition is much more precise. What's interesting for us is that to every stochastic process corresponds a time-varying probability density. Actually, the converse is not true, in the sense that possibly different stochastic process to the same probability density can correspond to stochastic processes, but in our work, we are interested in the probability density. The time evolution of the probability density can be studied to the Fokker-Planck equations that are these partial differential equations. They are also called Kolmogorov equations in the mathematical literature, and where we have that the differential operator L has this form and is nothing but the adjoint of the infinitesimal generator of the stochastic process. So these densities can be studied. And as an example, here I'm showing you a realization of a stochastic process of an SDE, the x of t. Of course, speaking about stochastic processes means speaking about a collection of random variables. So we have different realization of the same stochastic process. Different colors corresponds to the different realizations. And what we have is that we can study the evolution of the probability density at different time instants with the Fokker-Planck equation. So for example, if we zoom in here, if we fix time instant 0.1, we will have a certain density. While if we study the density of the process at time 9.5, we will have another density with a wider variance. It's not really relevant. And we can study the evolution from here to here using the before mentioned partial differential equations. Okay, so this concludes the crash introduction to SDEs, all that was needed. And now I want to spend some time speaking about optimal transport and generative modeling. So we consider the problem of generative modeling under the broad perspective of optimal transport. The idea is that we want to transform a simple starting distribution Px into the target data distribution P data. Data can be anything, images, we will see later, or whatever. Now, what I mean by simple, I mean something from which you can easily draw sample from, like a Gaussian distribution or a uniform distribution. We can cast the problem of transformation by considering a transformation cost and consider the optimal transport cost, that is equation 3. So we want to optimize this T, where we select the joint measure constrained to the fact that the marginal, one of the marginal is PS and the other marginal is P data, that minimize some given cost function C of X and Y. Okay. This is interesting, but the problem is that there is, in general, for the case we're interested in, no closed form solution. So here I want to stress that actually one of the solutions to solve numerically this problem corresponds to the well-known Wasserstein-Ganz, and is achieved by dualizing the cost. So what you do is you can write the dual and actually have equation 4 in which you transform the cost into a maximization problem over phi. Phi is the set of functions that satisfies certain technical requirements like Lipschitz constants and so on. What's interesting is that intuitively what you have is that you have the expected value of the metric phi of x when the input is drawn from P of S, minus the expected value of the function phi where the input is drawn from P data. You can take a step further and actually introduce an auxiliary generator that maps from PS to PI, whose goal is to minimize the distance, this distance. And then you have equation 5. Now, this corresponds to the, if you look for Wasserstein-Gunn on Google, probably you will find something like this, where the scheme represents the working mechanism of the training of generative adversarial networks. So what you have is that you have a generator that takes a noisy distribution, PS, this is white noise, transform it into an intermediate distribution, PI. You have data from a data distribution. In this case, I'm considering digits. And you have the phi statistic network that computes that computes equation 4. So the goal for the network is to maximize this difference, while the generator tries to minimize it. If this is achieved, this means that, I mean, if you write the Frechet derivative, you have that a stable solution is that Pi is equal to P data. And this is called adversarial because the generator tries to fool the discriminator. Okay. The generative adversarial networks have their problems, and actually another way to solve the problem is to introduce the optimal transport problem, is to introduce an entropy regularizer. So we write again the optimal transport cost, and we include epsilon, the entropy of the joint distribution. And by doing so, we can actually use a different approach and actually study the dynamical version of the optimization problem. So instead of simply, this is it is called static because we have a unique jump from PS to P data. Actually, what we can do is we can study the paths pi t such that the starting distribution is PS and the very final marginal is P data, and minimize the KL divergence between pi t and Qt, where Qt is, for example, the path measure of a Brownian motion. So the link from here to here is just to include the time dimension. And it's possible to show that solving these is equivalent to solving these. Okay, this is interesting, but why should we do so? Because, and here we get closer to the usage of stochastic differential equations. Actually, it's possible to solve to show that solving 7 is equivalent to solving the stochastic optimal control problem 8. That means minimizing the expected value of the norm of the cost of the control u, where the control u is in the stochastic differential equation. dx of t is equal to u of x of t plus the Brownian motion term, constrained to initial value sampled from PS and final value at a given time t distributed according to P data. Okay, so we are getting closer to the usage of SDES, but it's still not clear how to solve this analytically. The problem is that we don't know what kind of phase U has, and actually it's possible to derive, this is yet a step, another step towards the solution. It's possible to show that the optimal control is of the following form. So epsilon, the gradient of the log of phi of x and t, where actually we have that phi and phi at solve this system of partial differential equations with the given boundary conditions. So intuitively, here you have the Laplacian because we are considering a diffusion. If you consider a more generic SDE, you will have also the other divergence term for the drifts. But the point is that if you're able to solve this equation numerically, you can get the optimal control and solve the optimal transport problem. Now, what is the problem is that in our case, we generally deal with data that is very high dimensional. So a numerical solution of this partial differential equation is it's really hard, also considering the boundary constraint. So it's still difficult to solve. And then the problem can be recast in a different way. And this slide, it's really important to understand the link between Schrödinger bridges and diffusion or score-based generative models. So the three ingredients, also useful later, that we need to solve the problem are the following. First, the reverse of a diffusion process is a diffusion process. So whenever we have an SDE of this form, if we consider the reverse of this diffusion process, this is a result by Henderson, you will see in the bibliography in 1982, you have that also the reverse is a diffusion process. Of course, you have to take care technically about what does it mean to have a Brownian motion that goes backward in time. It's basically an SDE with minus the drift plus this term here that is nothing but the gradient of the log of the density of the starting process at time t minus t. So if this SDE evolves from time 0 to time big T, the reverse of this diffusion process is equivalent to this SDE. Actually, we're interested in paths in general, so it will be easier to prove stuff. We're not interested in the SDE per se, but in the induced densities, since we care about generative modeling. The second element is that actually, if we have a single constraint dynamical transport, we can use a disintegration theorem that tells us that if we want to minimize the KEL between pi of t and q of t when we have a single constraint, for example, the starting distribution instead of the ending distribution, you can actually split this KEL into two terms. This term here will be fixed and unsolvable. This is the KEL between PC and Q0, the density of the margin of Q, and this is fixed. And what you have here is that you have the other term is the expected value of the conditional of the KL of the conditional densities given initial conditions averaged over PC. Now, why is this important? Because by doing some math, it's possible to show that actually the solution is to match the dynamics of pi of t to the conditional dynamics of pi of t to the dynamics of q of t. And finally, the third ingredient is that whenever you have double constraints, one of the solutions is to iteratively solve the single constraints, alternating the two problems. And you can actually study the convergence. I mean, we can discuss later at the end of the presentation that for the moment, just assume that the whole process converge and solve the optimal transport problem. So to get closer to the real application, what we have is that the solution can be obtained numerically with the following iterative algorithm. So you start from, you sample your initial condition from P data, you simulate the diffusion for a given time t, you estimate, you compute the gradient of the log of the density for all time instants, and you derive the first optimal control. And then what you do, so you solve the problem considering the first constraint, and then what you do, you revert the equation. You start from the other constraint, from the initial conditions from PS. You simulate the SDE, and what you do of this SDE, you again estimate the density and update the drift by reversing the original drift and considering this is just an application of this process, of this property, an iterative application of this process. Property and so on up to infinite time steps or a number of steps that gives you a desired accuracy. Okay, so in principle, this is the solution. The problem is that obviously you cannot afford to spend an infinite amount of steps to estimate these densities. And so actually, and here I want to introduce finally the score-based SDEs, you can stop after some steps and hope that the solution that you get is good enough or close enough to something useful. And actually, one way to interpret this is to select T that goes to infinity and introduce score-based stochastic differential equations or diffusion models. Now, I want to stress that this is not the way in which score-based models are usually introduced in the literature. They're introduced at something else, but I like to draw the connection between the Schrödinger bridges and the score-based SDEs. So let's have a fresh start and introduce what are score-based differential equations. And these models are models built in such a way that starting, so in the kind of model we consider, we have two paths between data and noise. And actually, one of the two paths is easy, that is the information destruction part. So starting from an image, let's say I'm considering images, but any data distribution is fine, and going towards noisy distribution. This is easy. And but what we would like to do is to be able to do the opposite. So given starting from noise, to be able to transform this density into the data distribution. So going on this direction. Okay, so this is the starting motivation. And actually, then, as I just told you, we can say that we can have an easy path. We can use stochastic differential equation to simulate these two paths. And actually, if we start, so the easy path, starting from data, we can reach a simple destination x of t by considering, for example, this diffusion process, dx of t, alpha x of t plus the Brownian term component. Here I'm considering alpha and g constants, but everything I say is valid also for time varying, just to avoid messing too much with the notation. Actually, what's hard and interesting is to do the reverse. So the reverse process, so to start from the noise and to get back to the data. And thankfully, as we just saw, the reverse of a diffusion process is a diffusion process, as Anderson showed, in the form of 12 when we consider this kind of diffusion. So we have the reverse of the drift, the Brownian motion term, plus this term here. And here is where I just wanted to spend a second on the name score-based SDEs. In the literature, the gradient of the log of the density is usually referred to as score. So the name score derives from the fact that we use in the drift this term here. Okay. So by rewriting by having again the same picture as before, we can have that we have that this path is simulated by the diffusion, and as you can understand, this is an easy path. So to go from data towards noise, it's easy. Actually, by using the reverse of the SDE formalism, we can also do the other difficult and interesting path, that is going from x of t, from the distribution of a noisy distribution to the data distribution, where I want to underline that the red term here is the score. Okay. So to get closer to the application, we have actually some problems that we are currently investigating in our research. Now, in principle, P of x and t is easy if and only if t goes to infinity. So we reach the steady states. For example, for a diffusion, you reach the univariate Gaussian distribution. But in practice, you cannot have an infinite t. So what happens when you select a large but finite t? You will have errors, hopefully small, but at least something that is implementable. So this is actually a very interesting point. The second point on which this presentation will focus more on is that actually we don't know the score function. So one possible way to have the score function is to use, and here is where we have the parametric, the neural network, is to do a parametric estimation using the cost function 13, that is nothing but an expected value over time instant distributed uniformly, initial conditions, and the value of the stochastic process of the norm of this neural network S theta, minus the gradient of the score, the conditional score, log of P of x of t given x0 and t. Now, if you write the functional derivative of this, you come up, you can see that the solution, the optimal solution is S of theta is actually the score that we want to have. Okay, so now we have something that can be at least from outside, it seems something that we can compute with a Monte Carlo integral. And so for the moment, assuming that that we had access to this S of theta, the story now, yet another step closer to the application, is that we can starting from a noisy distribution, we can get back to the data distribution by using the neural network here in the SDE simulation instead of the unknown score. Okay, but now it's time to actually spend some time. I just told you, let's assume that you can minimize this cost. It's actually useful to spend some time in understanding that actually score-based SDE at training time are nothing but denoising autoencoders. So the recipe is the following. So if we select affine SDEs, like what is done in all the literature, actually the diffusion path, so going from the data to the noise, is simple and known. So what we have is that actually a conditional sample, the random variable x of t given x0, can be written as k. This is the mean k of t x0, where k of t will depend on the diffusion and the time t, just a constant. Sorry, at time varying quantity, plus gamma of t, again gamma just something that we can compute analytically, and w, where w is standard Gaussian noise. So we have a conditional sample. We can draw a conditional sample without the need to simulate in the diffusion SDE. And we can, what we do in practice to minimize the cost is to build an augmented training data set. So for all the samples in our training data set, and all the t's distributed uniformly in 0 big T, plus many realization of the random noise, we build the augmented data set that is composed by couples x of 0 and x of t, the noise the conditional on x of 0, when the sample is drawn according to this. And I want to stress this, that training the cost function and getting the optimal S of theta is nothing but the denoising autoencoder. The problem is the same as the one of a denoising autoencoder trained on the augmented dataset R. Besides from reparameterization, as we'll see in a moment. So actually, in terms of building blocks, what you have is that you start from your sample from the data set. You sample uniformly t between 0 and big T. You get a conditional sample x of 0. And the goal of S prime, a reparameterization, is just to get back to the original image without noise. So at training time, you can do so because you both have these and the noiseless image. And at testing time, you will also obviously only have the noisy version. So the S of theta is trained on the augmented data set to be able to denoise the input image. And actually, it's possible to show that the score is just a reparameterization. So what is done in practice, what I did in practice also in terms of code, is that you write a denoising autoencoder and then you just reparameterize the output as you actually in these models, you want to estimate the noise, but obviously estimating the noise or estimating the true signal are two complementary things, of course. Okay, so this is how you train your model and you estimate the parameters of your network. And now it's time to get closer to the application, to the sample generation. And actually, we can understand the process of generating sample as a recurrent denoising problem. So let's consider samples generated starting from the simple distribution, the noise distribution. So x of 0 sampled from the noise distribution at time 0. What you do is you iteratively estimate the noise using the denoising autoencoder. And then you update numerically. This is just an example of an Euler step. But if you're familiar with SDE integration techniques, you can use Runge-Kutta, you can use really any other SDE numerical integration scheme. And you update the value of the process using two components. So x of t, this is the analytically known diffusion part, alpha x of t and the Brownian motion term. And what you have is that you have also the role of the denoising network. And then you update you increment by a non-zero, by a small step size, the value of t, and you simulate the SDE up to the point where you reach the final time instant p. Okay? To be yet another step closer to application, I want to show you the building blocks of these. So what we have in practice is that once you train the model, so we saw what does it mean at training time to estimate the score network. Let's assume now that we have the train network. What you do in practice is you build a recurrent scheme in which the value of the stochastic process x of t is fed to the two branches. This one here is the analytically known branch. This branch here is the one that approximates the score. And you update the value of the stochastic process x of t, and you feed it back for the next time instant in the loop. So starting from noise, this means that you start from a noise sample, a white noise sample. You feed it to the branches. The value of x of t is updated. So what you get is a slightly less noisy version of the original input that is starting to get closer to something like a 9. This, at the next time instant, is fed back to the architecture. And what you have is that the process is repeated. So x of t is fed into the branches. The value of the stochastic process is updated. What you get is a even less noisy version of the input that once again is fed back into the architecture, and you end up finally with a sample from p data distribution. Okay, so this is how, obviously this is for example, an implementation of an earlier scheme, but as I told you before, you can have many different schemes. And the other point I want to stress is that actually, so in the beginning, I promised you that we would have been able to estimate the density. So I want to discuss about how it's possible to compute the likelihood using these models. So the first ingredient is the following. The ingredient is that different processes can correspond say the same density evolution. So for example, we have the diffusion SDE 15 that is of this form, where the initial conditions are drawn from p data. That corresponds to this partial differential equation with the given initial conditions. But actually what we have is that also this ordinary differential equation where we have this extra drift term here, where p is actually the solution of this PDE that induces the same density evolution. So we can use this trick actually, since we are only interested in the densities, we can use this trick, as we will see in a moment, to estimate the likelihood. So as a trick, we consider as I just told you, the ordinary differential equation with deterministic, the ODE with this drift. And actually, here is the typo, this should be the not partial. If we consider the derivative of p of x of t, where x of t evolves according to this with respect to time, what we have is that, okay, we have the derivative with respect to the first element. So the gradient, the transpose of p of x of t, so gradient with respect to the values x times dx of t, the t, so the chain rule, obviously, where we start to see that these will be equal to, by definition, to h, plus, and when we apply the derivative to the second element, we get the usual Fokker-Planck equation. Actually, since it's deterministic, it's called UVIL, but it's not relevant. And if you do some math, some of the terms simplify, and what you get in the end is that you have the divergence of the field h of x of t, and outside of the divergence, you have the probability p. Okay? So if you just simplify, if you do yet some other simple tricks, we have that log of p data of x of 0 is nothing but log of p data a log of p of x of 0 at time 0 by definition. And using this trick here, we can actually invert it and write the integral and have that the log of px of 0 at time 0, so the density, will be equal to the density to the log of p of x of t at time t, so our almost Gaussian-like distribution, plus this integral that we can estimate numerically. So to compute the likelihood, it is sufficient to simulate this ODE and accumulate the values here to get a final estimate. Okay, so what can these models do to lighten a little bit the mood? Actually, these models can be used to do image generation. So these models are, I'm going to show you examples on the image domain. These faces have been generated, are taken from one of the mentioned from all the resources in the bibliography. These faces have been generated starting from Gaussian noise and following the denoising process that I showed you before. So as you can see, these models are really powerful and flexible and are able to model really complex densities. So if you're interested in generating realistic data from complex densities, these models can be used. Or, for example, by slightly modifying the SDE and including an extra control factor, you can have class-conditional generation. So, for example, in this data set here, CFAR10, you have many different classes like birds or deers. And what you can do is that you can actually tell your model to generate samples conditionally on a given class. So you can generate birds conditioning on the label, or deers using a similar process. So this again can be a useful, in certain application, a useful feature. Or these kind of models can be used to do completion of missing values. So what you have is that, for example, you start from an image. Somehow you lose, in this case, some of the pixels. So the black pixels here are lost. And what you want to do is to reconstruct an image such that the value inside the unmasked value is preserved. And the other pixels are consistent in terms of the distribution with the starting image. So what you have here, you have different completion. So these are different realization because you have different samples. And the idea is that you can fill the missing values with and get realistic images that are consistent with the observed input. Of course, you can also flip the mask. I mean, this is just an example. Or yet another example, for example, when you have different channels, so in this case, color image, what happens if you want to colorize a grayscale image? You can use these techniques to colorize these images. Okay, so I want to spend some time discussing about the challenges. And actually, I want to stress that diffusion models are very recent. So the seminal work, even if of course SDEs have been studied since a long time, their usage in the generative modeling community first appeared in 2015. But actually, the bulk of the literature is really recent, only the last couple of years. So there is still a lot to do with these models. Why? Because there are many computational challenges. So something I want to stress is that this model are being studied since they outperform other competitors like GANs or variational autoencoders, but they are really computationally expensive. Just to give you an idea, for the research we are carrying out for the experimental campaign, we will need more than 1 month of computation on 8 to 16 GPUs. So one of the possible problem to be attacked, possible problem to be attacked is to be able to perform efficient samplings. This can be done either by building better stochastic differential integration SDE integrators, so studying SDE integrators that are suited for the diffusion we're interested in, or actually to design faster SDEs to speed up the generation process. Now, I want to stress that actually I really mean design SDEs, because differently from other scientific disciplines in which the SDEs are a model, in this case, they are just a tool and we can design whatever SDE we like provided that it's useful. Or the other problem is that actually the ending time t is not equal to infinity. So we are actively working on these, and actually selecting a t that is not infinity introduces a trade-off between model quality. So the larger the t, the higher the model quality, but also the higher the complexity of the network and the training time. The higher the generation speed, because you need to simulate the same SDE for a longer amount of time, and the larger the t, the slower the training, because in the end you need to train a denoising autoencoder. So when t is very large, you need to denoise data in a regime where there is a lot of noise for the vast majority of the time. And yet another point that is open is that current formulations are very specialized, and actually it would be interesting to study all these kind of models under the unifying perspective of optimal transport, to be able to mix together different properties of this model to reduce the computational cost, to combine together this kind of models. Okay, and for example, from another perspective, something that could be also interesting that is done in other generative models is to be able to go beyond single modality. That means having a multimodal lateral representation. So in this case, for example, we can consider, I don't know whether it's you can see it from the slide. So we have sentences and corresponding images. So we want to be able, for example, given a sentence, this small white bird, blah, 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 to generate an image that is consistent with the sentence that we have. Or to be able to do the opposite, like to go from vision to language. So given an image, to generate a sentence that is consistent with the image that we saw. So in this case, for example, the caption is, this bird is brown with white and very short beak. This has been done in other generative domain applications. We want to do so also in score-based and diffusion models. Okay, so finally, some conclusions. Generative models, as you have seen in this presentation, can be understood using optimal transport. So different models like Wasserstein-Ganz, Schrödinger bridges, or score SDEs can be cast as different ways to solve the same optimal transport problem. Score SDEs have better generation quality than other competitors and allows us to perform flexible density estimation. However, these methods are in their infancy, and they are really computationally heavier than alternatives. And by heavier, I want to stress we're talking about order of magnitudes with respect to other competitors. And something that could be interesting is what about more generic spaces? So now I showed you, for simplicity, example on images, but what if we have data on Riemann manifolds or Hilbert spaces? Can this model be generalized to these kind of spaces? And so I just want to conclude by saying thank you and saying that we are actually hiring and looking for collaborators